So one was this way, right? One was this way from the magnets itself, right?
Explain that again.
Yes. What are you saying, Aisha?
Can you explain this again?
Oh, okay. Okay, so what I told you earlier that whenever some induced current is generated, so it opposes the change, right? It opposes the change, which means that this induced current will try to force this magnet to go in the opposite direction. It is coming in this direction, so this induced current will try to oppose this change. Right? This is what I talked about, right?
Yes.
So this north is coming towards it, right? This north pole is coming towards this circuit. So what current should generate so that it opposes this north pole? So what opposes the north pole?
Not more.
North pole, right? So it should create this kind of north kind of pole, right? So which means that the current direction would be, this is what, clockwise or anti-clockwise?
And
Anti-clock, anti-clockwise, right? So this is how this current would be induced. Understood?
yes.
And now, and then after that, I talked about that. Let's say that the magnet is going in the opposite direction. It is going away. So what this current should do? It should attract or repel to oppose the motion.
It
Yes,
should adjust.
attract. So this is north and south will attract. So that's why this direction would be the induced current. Understood?
Yes.
And similarly, if south is coming, then south will be created so that it will repel south. So this was the idea, right? Now the second case is that, so the case second is that we have a magnetic field, right? We have this magnetic field. So in the previous case, what did you do? In the previous case, you were moving the magnets, right? Now, in this case, you have a fixed magnetic field. So this is what direction, Aisha?
Inwards.
Inwards, right? So this is inwards direction. And you are bringing a coil in this direction, right? You are bringing a coil in this direction. So what will happen to the electric flux? Flux will decrease or increase. So let's say this is case first. This is coming out. So this is case second, and let's say this is the other one, right? Okay, this is third one. So now in the first case, right? In the first case, flux is decreasing or increasing. So when it goes in, the amount of magnetic field it will experience will be increased or decreased.
Increase.
So flux is increasing or decreasing. Remember, flux is what? Flux is BA cos theta, right? And theta is 0, so this is BA. So whenever magnetic field is increased, your flux will what?
Increase.
Increase. So for case first, flux is increased, right? So flux is increasing, which means that induced current will try to what? Decrease the flux.
Yeah.
So if induced current is trying to decrease the flux, which means that it will try to decrease the magnetic field, right?
Yeah.
So if I have in the downward direction, if in the inside direction I have the magnetic field, so to decrease the magnetic field, I'll have to create another magnetic field which is opposite, right?
Yeah.
So induced current will decrease, will try to decrease the magnetic field, right? Which means that, let's say that, so in what direction the magnetic field will be created by this induced current? So this is downward, not downward, but inward. So what would be the direction of magnetic field created by this loop?
Outward.
Outward. Absolutely right. Good. So the this loop, this, let's say ABCD loop, will create an outward magnetic field, right? So if magnetic field is outward, so what will be the direction of the induced current? Clockwise or anti-clockwise? Put your thumb in the direction of the magnetic field. What is the direction your fingers are giving? Curled fingers are giving.
Clockwise.
Yes,
Clockwise.
clockwise. So if you put your thumb in the direction of outward and then you curl your finger, so what is the direction that you're getting?
Anti-clock.
Yeah, anti-clockwise, right?
Yes.
So in this direction, right? So, and you can see that, you are putting your thumb in the upward direction and you are curling, right? So this is anti-clockwise. And you can also see from the current. The current is going in this anti-clockwise direction. So what is the direction that it is giving, the magnetic field?
Outward.
Outward, right? So understood about the direction.
Yes.
So let me write the direction. Direction would be A, B, C, D. So direction of induced current will be A, B, C, D. Understood? Now, now let us talk about case two. Right. So this flux, this loop is going outside, right? It is moving away from the magnetic field. So flux is increasing or decreasing?
Decreasing.
Flux is decreasing, right? So flux is decreasing. So now what this induced current will do? Oh, who got disconnected? Sad got disconnected. So this induced current will try to decrease or increase the magnetic field.
Increase.
Increase, will try to increase the magnetic field. So now you tell me what would be the direction of the induced current, clockwise or anti-clockwise? what would be the direction of the, because you know that direction of induced magnetic field is this. So what would be the direction of current, induced current?
Mm.
Yes, Aisha.
Is it clockwise?
Clockwise. So be confident. Do not say is it. So if you're confident, say that it is clockwise, right? So if you can check that also. If the magnetic field is clockwise, then what would be the direction of magnetic field you will get? If you curl your finger, then what would be the direction of the magnetic field? Outward or inward?
Inward.
Inward, right? So you are correct. Why so confused? So direction of induced current will be, let me write it as this is P, right? This is Q, this is R, this is S. So will be P, Q, R, S. Oh, did Sadh join? He's still joined. Hmm. Understood, Aisha? Any doubt up to this point?
No, sir.
Okay. So now, third case. So the loop is inside the magnetic field. So can you tell me that flux is changing, increasing, decreasing? What is happening with the flux? It is moving inside the magnetic.
Increasing.
Increasing, it is same, right? All because area, you see area is same. So same electric field lines are going, right? In here it is also same, in here it is also same, because this is uniform magnetic field. So in here the magnetic field is same, in here magnetic field is same, in here magnetic field is same. When it was going in this direction, so the magnetic field, let's say it reached here. So magnetic field has increased. Now it has reached here. So magnetic field has increased more. But let's say it is coming out. So in here the magnetic field was something and then it has come out to this point, so it has decreased. So number of field lines crossing through this area is decreasing. But in here the same number of magnetic field lines are crossing, right? Understood? At this area, whenever in this area, this loop is in this area. So it will have the same magnetic field line all across this area, right?
Yes, sir.
So flux is same. So no induced current. Okay. See for this one. Let me draw this to clarify my point. So let's say that initially the loop was in here and it was moving in this way, and you had magnetic field uniform. So now it has two electric field lines, but it has moved to this area. It has come to this point. So now it has four electric field lines. Now it has come to this point, right? So it is going inside. So now the magnetic field lines have increased. So in this case, you can see that it is increasing, right?
Yes, sir.
And but whenever it is inside, so now it has come inside. So this is same, again this is same. So it will remain same. Whenever it is moving inside, So magnetic field lines will remain same, right? So,
Yes, sir.
so that is why flux is not changing, so no induced current. Okay, did Saad join? Oh, he again got disconnected. So you please note it down and then we'll start the new topic. So these were the two cases of uh, calculating the or finding the direction of induced current. Please note it down. In the first case, magnet was moving. In the second case, the loop is moving. Whenever you have noted it down, please tell. Whenever you have noted it down, please tell.
Well,
Okay. So now let us study about motion. So in your school, what chapter they are currently doing?
now they completed EMI today, and they are going to start alternating current.
Okay, so they have completed the fifth chapter. Yes, the fifth one.
No, so they completed the sixth one today.
Oh, sixth one they have completed.
Yeah,
Okay, so we have how many topics remaining? We have this motional EMF, then induction, and it has of two type, mutual and self, and then generator. So we have three, four topics remaining, right? So let us complete that and yeah. So because fifth chapter is not that long, so fifth chapter can be completed in two classes itself. So yeah, and I will provide you. Okay, but before that, let me send you. So this is a practice question, right? So You guys, please which one? I'm sending to it to the group. Please practice that. One. Okay, I've sent it to one group and there is another. Did you get the PDF that I have sent? Yes. Uh, practice. So I've sent it and you may find it in WhatsApp. So this is the next topic, right? So what do you have? So you have a magnetic field, uniform magnetic field, right? And then you have a circuit, and then you have a circuit. So this is a wire, okay? This is a wire of length L, right? So you have this P, Q, R, S. So only this QR length is moving, right? This point S, P are fixed. So these points P and S are fixed, only this line is moving with, let's say, velocity V. Okay, so this motional EMF says that whenever you move this wire, conducting wire, so an EMF will generate, right? And that EMF is generating due to this movement of this wire. So that is why it is called a motional EMF, right? So an EMF is generated due to the movement of the wire PQ moving with velocity, right? So this is the idea, and we already know that. What do we know that? What is the EMF? Induced EMF? What is that? What is induced EMF? Yes, Aisha. What is induced EMF? The
Change,
Faraday. Yes, yes. What?
change in flux by change in time.
Yeah, absolutely right. So minus of d phi by dt. Absolutely right. Right. So let me write it. So minus of d phi by d. Right. This is what is the induced EMF, right? Now we also know that this is, let's say, so this is length x, and this is a variable length, because if I am moving this wire in this at this point, so now my length x has become this, right? Understood? So
You can explain?
this, yeah, this length is moving, but this length, which is L, this is fixed, right?
Yes.
So what is my flux? Flux is what? This is an area. PQRS is an area. So what is the direction of the area vector? Let me write it as this is BA cos theta. Right? This is the flux. Right, Aisha?
Yes, sir.
So what is the direction between area vector? Area is this, right? PQRS is the area, right? So PQRS is the area. So what is the direction of the area vector? This is a plane, PQRL plane, right? So you have, so this is your area, PQRS. So it is in this direction, inward or outward?
Mhm.
Inward, right? And what is the direction of the magnetic field? What is the direction of the magnetic field? You can see it from here,
Inward.
inward. So theta is how much? Both are inward, so 0 degree, right? Understood?
So could you explain how A is inward?
Oh, okay. So you see that this is the PQRS plane. This is the area, right?
Yes.
And the direction of area vector, the direction of the area vector is always normal to the plane. So I am calculating this area, right? This area. The
Yes.
normal to this plane is inwards, right? If I was calculating the backward area, then normal would be outward. But I am calculating this area. So
But how we know if it is the backward or
yeah, so you see that I am taking the direction PQRS, this one, right? I'm not taking like PSRQ, this area. So I'm taking PQRS area, right?
yes,
So then it is inwards. The normal to the plane is inwards, right?
yes,
So that is how, and your magnetic field is also inwards. So this is also inverse, which means that both the direction are inverse, so we have theta equal to 0. Understood? Understood, or do you have any confusion again?
yes, I got it.
Okay. So now you tell me what is the area of PQRS? What is the area? What is the area of PQRS? See the shape. Yes, this is a rectangular shape, right? What is the area of rectangle?
And then do X.
Length into breadth, right? So what is the length?
Length is X.
Length is x and breadth is L. So you can see that in this BXL, what is a constant and what is variable?
L is constant.
Yes, L is constant, magnetic field is also constant, right?
Yes.
So if I put the value of flux from here, let's say this is what? From here to here. So what I will get? I'll get minus of d of BXL by dt. But I know that V and L are constant, so I can take it outside. So I will get minus of BL and dx by dt, right? So dx by dt is what? Dx by dt is rate of change of distance, velocity, right? So
Yeah.
this is velocity. So I will get minus BL. So this is what is called the motional here, right? And this minus sign represents the length law, right? So this induced EMF will try to change the motion, right? So that is why this is the motional. Understood?
Yes.
Okay. And if I calculate the current, so current would be E by R, which is minus BLV by R. Okay, so this is the induced current. And if I calculate the direction, right? So to calculate the direction or to calculate the polarity of this induced EMF, what would be the polarity, right? So this is the polarity of EMF. One is the higher potential, is this one is the lower potential. So what is the polarity of this EMF, right? And how do we calculate the polarity? So we calculate the polarity of, or to calculate the polarity of induced EMF, we use right hand palm. So this is not a conventional, remember this is not a conventional rule, but this rule will give you the direction. Calculate the polarity of induced, we use right hand palm, right? So what do we do in right hand palm rule? So this is the diagram, right? And remember, so what is the direction of the magnetic field? What we do is that we put our fingertips in the direction of the magnetic field, right? And our thumb in the direction of the velocity. So can you tell me what is the direction of the palm I am getting? Can you tell me? So the
The
idea is
point.
that you put your fingertips in the magnetic field direction, which is inwards. So magnetic field is inwards, your velocity is right. So what is the direction of the palm?
Upward.
Upward, right? Upward. Did you say upward?
Yes.
Absolutely right. So which means that that will be the direction, or that will be the higher potential. So upward would be the higher potential, and lower, this would be the lower potential. So, oh, Mariam is joining now. Okay, so this is higher potential, this is lower potential. Is this part clear?
Yes.
Clear, Aisha?
Yes, sir.
Okay, so Hello, Mariam. Assalamu alaikum.
Walaikum salam, sir.
You are so late. What happened? Did you get somewhere? Stuck somewhere? Did you get stuck somewhere?
No, sir, actually, there was some problem with Wi-Fi and I forgot.
Oh, okay. Oh, no worries. So we just started this motionally, right? So we are studying this motional EMF, which says that whenever in a circuit you change when you move the wire with some velocity, then there would be some induced EMF. So that EMF is due to the motion of that wire. That is why it is called the motional EMF. So now we were calculating the polarity of the motional. So yeah, so if you have this circuit like this, so can you guys tell me what would be the direction of the current? From where to where the direction of the current goes?
From positive to negative.
Positive to negative, from higher potential to lower potential. So this is the direction of the current, right? So the current will go from here, it will come here, right? And then it will come back. So this is the direction of the induced current, right? And this is the direction of the polarity. Is this part okay? So yeah, this you were not here, so let me say this again to you. That Mariam, we have this structure. We have this circuit, and in this circuit we can only move this wire. The other things are fixed, and it has a constant uniform magnetic field in inward direction. And we are moving this wire with velocity v. Okay. So then due to Faraday's law, some EMF is generating, which is this field. And to calculate the direction of the polarity of this EMF, we use the right hand palm rule. So what do we do in the right hand palm rule? So you see that velocity is in the right direction and magnetic field is inside. So we place our fingertips in the inside direction and thumb in the direction of velocity. So direction of velocity is right, fingertips inside. So you are getting the direction of the palm in upward direction, right? So the of the polarity of this circuit would be, this would be the higher potential and this would be the lower potential. So your palm gives the direction of the higher potential, right? Did you understand, Mariam, the right hand palm?
Yes, sir.
Okay, so let me write this, that you place your fingertip in V direction, magnetic field direction, and thumb in velocity direction. The direction given by palm will be positive turn or higher potential. Okay, so now you guys please note it down and then we'll calculate the other. And if you guys have any question, please tell. And whenever you guys want me to scroll down the screen, guys, please. Yeah, whenever you guys want me to scroll down the screen, you guys please tell. Yes, noted up to this point.
Well, sir.
Okay, so note down this. And whenever you guys have completed the pre-set, done. And Aisha, what about you?
Done, sir.
So now the next thing is magnetic force by motional EMF, right? So we have this circuit, and this is the direction of the magnetic field, and this is the moving wire, right? And the current is going in this direction. Okay, so you guys tell me that this is 3 volts, Inside is the magnetic field, right? Current is in this direction. So what would be the direction of the magnetic force at this point? What would be the direction? Yes. What is the direction of the magnetic force in the conducting wire?
Sir, can you please repeat?
So this is a wire, right? Let's say this is AB wire. Current is flowing in this direction. Magnetic field is inside. So what is the direction of magnetic force on this wire? Hmm. What is the magnetic force on current carrying wire? Z. Z is outward. Z is outward. So you are saying this direction. Hmm? What is the magnetic force on current carrying wire? Perpendicular to this. Okay, yes. Perpendicular. So L cross B. L is upward, right? L is upward. Magnetic field is okay. L is upward, right? L is upward. Palm is magnetic field. We curl our finger. What is the direction that we are getting? Yes. What is the direction we are getting?
minus
This
X.
one, right? Is this correct, guys? Understood this part? Why am I getting this?
Yes, sir.
Understood, everyone? Yes, guys. Understood.
Yes,
So your voice is speaking.
My voice is lagging, breaking.
yes,
Yes.
Yeah. So I have my fingertips in the L direction. L cross B. B is palm, right? If I curl my finger. So this is the magnetic force that I am getting, right, guys?
Yes, sir.
So the left direction. Now you see that this wire is moving in this direction, right? Velocity is this direction. Your magnetic force is in this direction. So this induced EMF will try to oppose the motion of this velocity. Am I correct? Correct, guys. So this induced EMF will try to oppose this motion, right?
Yes, sir.
So if I want to have a constant velocity, right? This is pulling me in this left direction. But I want this velocity to be constant. Why I want this velocity to be constant? Because my current is what? Can you guys tell me what is my current? My current is minus VLV. So let us skip, let us just try write the magnitude, forget about the direction. So my current is VLV by R, right? Resistance is fixed, magnetic field is fixed, this L, length of the wire is fixed, this V is changing. This is decreasing and this is going to be zero. So if this V is changing, my current is what? Changing, right? Fluctuating, right, guys?
Yes.
But I want this current to be fixed, right? I want this current to be constant. So what should I do? If I want this current to be fixed, I want this velocity to be fixed, right? To have the current fixed, I have to fix this velocity, right? But this magnetic force is decreasing this velocity. It is pulling this wire in the left direction. So what should I do so that my velocity is constant, guys? What should I do? Yes, what should I do? Aisha and Maria, I have this magnetic field which is trying to oppose this velocity, which is decreasing this velocity. So what should I do to take care of this magnetic force? What should I do? Yes, Aisha and Maria, any idea what should we do? Yes, right. No idea. Oh,
Yes.
okay. So let's say that if I apply a same force, external force, which is equal to this magnetic force. So this is external, right? So this external force balances this magnetic force. So this part and this part cancels each other out and I have this constant velocity. Is this point clear? Is this point clear?
Yes.
Okay, but before I calculate this external force, let us find the magnetic force. So FB is ILB, right? And these are perpendicular. L and B are perpendicular. So this is right sine 90, which is 1. I we have calculated. I is BLB by R. And this is LB. So this is B square L square V by R. This is my magnetic force. Understood, everyone? And this is, of course, with a negative sign because this I is minus BLB by R, right? But I have just considering that, right? So is this part clear, everyone? The magnetic force? Because I have calculated the induced current. This is BLB by R. So then my magnetic force is this. And I am saying that I want to have this velocity to be fixed. So I am applying an F external, right? This is equal to minus of AC. So this F external is magnitude of this F external is how much? This is V S square L square V by R. Is this part clear, everyone? Is this part clear?
Yes.
Because both the magnitude of F external and F magnetic both are same, so that they cancel out each other because they have opposite direction, and I get a very constant velocity so that I don't get any fluctuating current, right? So now I have calculated the force. Now I have to calculate the mechanical power. Right. So I have to calculate how much power I am exhausting, right, to have the fixed current. So mechanical power is how much? This is dW by dt, rate of doing work. And we know that this is F and dt dx, right, by dt. So this is F V, and this is external. So F external is V square L square V by R and then V. So this is V square L square V square by R. So this is my mechanical power, right? Because this external power I am supplying to have a fixed amount of induced current. Is this part clear, everyone?
Yes. Okay.
Okay, so you guys please note down from here and then we'll do some questions. So this part you guys have noted, so note down from. And whenever you guys want me to scroll down the screen, you guys please tell.
Thank you.
Yeah. So whenever you guys have noted it down, please tell. Done. So what is this mechanical power? This is the power you are supplying to this circuit, right? This is the power you are supplying to this circuit, right? Now, what is the electrical power? So electrical power is due to the induced current, right? Electrical power is I square R, right? This is the electrical power. So I, you have already calculated, this was BLP. This is how much? I is PLV by R, right? This is PLV square and by R and then R. So this is how much? This is B square L square V square by R square and then R. So this cancels out and this is equal to what? Which is exactly equal to mechanical power, right? So you see that your mechanical power is equal to the electrical power, right? So this is what Lenz's law says, right? And it is saying that whatever the power, whatever the energy you are supplying, the same amount of energy is converted to the electrical power, right? So which means that energy is conserved. This is part clear. So
Yes.
whatever power, whatever mechanical work you have done, so that is converted into the electrical power. So this part tells us that this part tells us that energy law of conservation of energy is obeyed by the Lenz law. Okay, so this you guys please note it down. And what did we learn from the emotional EMF? So we know that EMF is BLV, right? We know that I is BLV by R, and this has a negative sign, right? So, and then the force, magnetic force is how much? This is B square L square V by R, right? And make power. Power is B square L square V square by R. So these are the four things that we have to remember in motion, right? FB was what? V square square V by. So please note it down, and then question I will skip because I have less time. So I'll start another topic. You guys please note it down. And if you guys have any confusion, so please ask. Got disconnected. Mariam got disconnected. Okay, whenever you want me to scroll down the screen, Aisha, you please tell. I wanted to do few problems, but will not get time. So what I will do is that I will start another topic and then
In terms
we
of
will do the questions later.
done, sir.
Done. So Maria just yes, Mariam, please take the screenshot and then we'll start the topic, right? So how much did you note it down? How much you have noted, Mariam? Okay. Oh, you have noted. So now let us understand about the new topic, which is mutual inductance. So what does it say? So let's say that if you have a coil, right? And what you do is that you switch on this coil, which means that some current will increase, right? So some current will increase, and the adjacent to this coil you have another coil. Okay, and this circuit is completed. So due to the increase in this electric current, right, there would be some flux generated through this area. There would be some flux due to this, right, there would be some flux due to in this area, due to this change in current, right, guys? Or due to this current, there would be some flux. So this mutual inductance says that this flux generated in this, let's say this is second circuit, right? So the flux generated in this second circuit would be equal to the current in the first circuit, right? So this flux generated, this says that the flux generated in the, let's say this is first circuit. In the second circuit would be proportional to the current flowing in the first circuit. Is this part clear? So this phi is, let's say in the second circuit, it is proportional to this current in, let's say, let me write it as I1. So this is I1. So this is I1. If I remove this proportionality, so I will get this constant. And this is called the conductance. right? So this is called the mutual conductance or inductance, not conductance, but inductance. Is this part clear, everyone? Yes.
Yes, sir.
So this M21 is the unit of this conductance. In this case, this is a mutual conductance. So we'll also learn about the self-conduct inductance. Did I write conductance? Because conductance is about the conductors, right? So this is denoted by Henry, right? SI unit of this inductance is Henry, denoted by H. Okay. Now, you guys please note it down, and then we'll understand about the example of a solid one. So just remember this, and then it would be easy to understand. Just remember this, that the flux generated in the second circuit would be due to the current of the first circuit. That is the important part. So this part we have to just remember, right? So whenever you guys have completed, please tell.
Yes, sir.
Yes, noted.
Yes, sir.
Okay, completed everyone.
Yes, sir.
Okay, so now this is very important. This one is very important. So mutual inductance in a coaxial solenoid. So we have, right, we have, let's say we have two solenoids. One is this, and then we have the smaller one. So two solenoids, right? Let's say this is S1, this is S1, and then this is S2, right? So let's take, and in this solenoid, current I1 is flowing, and in this solenoid, current I2 is right. So let's say that if I1 is flowing, so due to this I1, there would be some flux generated in this second one, right? So this is M21 and I1, right, guys? Is this part clear? So
can explain again.
yes, Aisha, what did you say?
Can you explain again?
Yeah. So there is some flux, right? There is some flux generated in this. So due to current I1, there is some flux generated in this. Flux generated in this inside S21 solenoid. In the second solenoid, due to this first one, there is some flux generated. Is that clear? And we know that flux is proportional to the current, right? So this flux would be flux generated in coil due to this I1 current would be proportional to this I1 current. Is this part clear, Aisha and Mariam? Is this clear?
Yes.
So we have this I1 current, right? And due to this I1 current, there is some magnetic field lines passing through this second one. So that is, if there is some magnetic field lines crossing through these areas, then there is some flux. And this is proportional to current I1. So that's why we remove the proportionality and we get this inductance, right? But this is for one turn. But if we have, let's say, N2 turns, so this would be N2, right? Total number of turns is N2. We have this I1 current flowing, right? So due to this I1 current, we have the flux in the circuit, and that is how much? That is M12 and I2. So if this part is clear, then you guys please tell. Flux generated in both the solenoids. Is this part clear?
Yes, sir.
Okay. So now we have to calculate the flux through this two one. Flux through this second solenoid. So we know
So your
that
voice
how
is
much
cracking.
or before we. My voice is cracking. Am I audible clear now? Am I audible clear now?
Yes,
Yes.
sir.
Okay. So flux is how much? That is B and A, right? So let's say the area of this solenoid is A, right? This is the area. Okay, same area. So this is A, and this is phi 2, right? So this is 2, this is 2, this is. And can you guys tell me that what is the magnetic field of a solenoid? If you guys remember or not, can you guys tell? Magnetic field of a solenoid. This we have studied. What is the magnetic field of solenoid? Aisha and Maria. Magnetic field of
You
a
not
solenoid. Mu
and
naught, yes, n line. Absolutely right. And remember, this is a small n. So this is number density, right? Good.
yeah,
So absolutely right. So what I will do is that, yeah, so what I will do is that, and remember this is the